We will continue with the third session of our conference with the title Inspection Methods, Laboratory Testing and Structural Analysis. And the first presentation is about Adobe buildings, earthquake resistance and their application in Turkey. There were three authors of this paper: Muhammed, Şükrü, YAVAŞ, Ayşe TELOİ, and Zekai, CELEP, all three from the Fatih Sultan Mehmet Vakif University in Istanbul. And Muhammed, Şükrü, YAVAŞ will now present the paper.
Yes. Thank you.
He is already there. Very nice. Okay, please.
Hocam, şu anda ekranımı paylaşıyorum o zaman. Değil mi? Tamam.
Yes.
Can you see my presentation right now?
Yes, we can see your screen.
Okay. All right. I'm starting. If you don't mind, I will be continuing with Turkish language. Merhabalar, ismim Muhammed, Şükrü, YAVAŞ. Bugünkü sunumumun konusu Türkiye'deki kerpiç binaların deprem güvenliği ve uygulamaları şeklinde olacak. If I say in English, Adobe buildings, earthquake resistance and their application in Turkey. Sunumun içeriği şu şekilde. İlk başta önceki çalışmalardan bahsedeceğim ve bir giriş yapacağım. Sonrasında kerpiç tuğla ve duvarlardan bahsedeceğim. Sonrasında kerpiç binaların dezavantajları nelerdir onları söyleyeceğim. Ardından kerpiç tuğlaların mekanik özellikleri nelerdir onlardan bahsedeceğim. Ve kerpiç binalarda dikkat edilmesi gereken en önemli parçalar olan çatı ve temellerden bahsedeceğim. Kerpiç tek katlı bir yapının basit bir nümerik analizini 6. bölümde yapacağım ve kerpiç yapıları için deprem güvenliklerine dair öneri kuralları da 7. bölümde söyleyeceğim. Sonuçlarla bitireceğim. Önceki çalışmalara bakacak olursak 2017 yılında zaman yaptığı çalışmada Türkiye'deki kırsal nüfusun %50'sinin kerpiç binalarda yaşadığını söylemiştir. Londra ve diğerleri 2013 yılındaki yaptığı çalışmada dünya kırsal nüfusunun %30'unun kerpiç yapılarda yaşadığını ve bu oranın gelişmekte olan ülkelerde %50 olduğunu söylemiştir. 2020 yılında Güler ve diğerleri yayınladıkları çalışmada 2019 yılında meydana gelen Denizli Acıpayam depreminde 572 tane yığma yapının tamamen çöktüğünü ve bunların pek çoğunun kerpiç olduğunu söylemiştir. 2017 yılında Bakşi ve diğerleri İran'daki Bam depreminden sonra kerpiç yapıların güçlendirilmesine dair deneysel çalışmalar yapmıştır. Geçmişten günümüze deprem yönetmeliklerinde kerpiç yapılara ait kurallar bulunmaktaydı. 1998 yılındaki deprem yönetmeliğimizin 11. bölümü tamamen kerpiç yapılara ayrılmış durumdadır. 2007 yılındaki deprem yönetmeliğimizin 5. bölümü yığma binalar için deprem kurallarının altında kerpiç yapılar için kurallar bulunmaktaydı. 2018 yılında yayınlanan ve en yeni deprem yönetmenimiz olan Türkiye Bina Deprem Yönetmeliğinde taşıyıcı duvar malzemesi olarak kerpiç malzemesinin kullanımına izin verilmemektedir. Bu çalışmanın amacı da kerpiç yapıların tekrardan Türkiye Bina Deprem Yönetmeliğine girmesi ve onlara uygun deprem kurallarının tekrardan gündeme getirilmesi şeklindedir. Kerpiç tuğla ve binaların üretimine bakacak olursak aslında gayet basit bir yöntem. İlk önce derin bir çukur açılır ve bu çukurun içine kerpiç harcı ve tuğlası için gereken malzemeler koyulur. Bunlar nelerdir? Kerpiç toprağı, saman ve sudur. Bunlar kürek yardımıyla karıştırılır. Kepçe veya diğer araçlarla karıştırılması önerilmez. Çünkü tamamen karışması için kürek en iyi yöntemdir. Hazırlanan harç el arabası yardımıyla ahşap kalıplara taşınır ve ahşap kalıplara dökülür. Belli bir süre bekledikten sonra bir gün deniyor. Belli bir süre bekledikten sonra da kalıplardan çıkartılır ve güneş altında her bir yüzeyi kuruyacak şekilde bırakılır. Burada dikkat edilmesi gereken bazı konular var. El arabasıyla harcı ahşap kalıplara getirirken hızlı olunmalı. Çünkü harç kuruyabilir. Eğer ahşap kalıp ıslak değilse bir miktar ıslatmak faydalı olur. Çünkü kalıptan daha kolay çıkmasını sağlar. Kurutulacak yüzeyinde düz olması gerekir ki bu da tuğlaların dikdörtgen şeklinde çıkması için önemlidir. Aynı malzemelerle kerpiç harcı da yapılır. Kerpiç harcının iki amacı vardır. Bunlardan bir tanesi kerpiç tuğlalar arasındaki bağlantıyı sağlamak. İkincisi de kerpiç duvarın düz bir yüzey görünümüne sahip olmasını sağlamak. Harç kerpiç duvara uygulanmadan önce duvar bir miktar ıslatılır ki kerpiç duvarla harç birbirine tek bir malzeme gibi davranabilsin. Kerpiç tuğlaları üretimi için en iyi zaman Mayıs ve Eylül ayları arasıdır. Diğer aylarda ise kerpiç tuğlalar yağmurdan korunmalıdır. Bunun için çadır ve benzeri şeyler kerpiç tuğlaların üzerine örtülür. Aynı zamanda bu çadırın etrafına bir hendek kazılır ki zemin suyundan da kerpiç tuğlalar bir sonraki döneme kadar korunabilsin. Kerpiç yapıların dezavantajlarına bakacak olursak, ilk başta su. Kerpiç yapılar yağmur veya sel gibi su maddelerine maruz kaldığı zaman kerpiç tuğlalar şişer ve parçalama ve dağılma sürecine girer. Ülkemizde bu sayıda çok fazla hasar mevcuttur kerpiç yapılarda. Bir diğer dezavantaj ise deprem. Deprem tüm yapılarda zeminde meydana gelir ve yüksek kat, binanın katlarına yukarı doğru çıkıldıkça artarak devam eder. Deprem kuvveti binanın kütlesine ve yatay ivmeye bağlıdır. Deprem ivmesine bağlıdır. Bu deprem kuvveti sonucunda basınç ve çekme gerilimleri meydana gelir. Binada güvenli olarak taşınabilmesi için yapı malzemesi basınç ve çekme gerilmesinin oluşan basınç ve çekme gerilmesinden büyük olması gerekir. Maalesef ki kerpiç malzemesinin basınç ve çekme gerilmesi düşüktür. Fakat belli katkılarla bunun arttırılması mümkündür. Mesela örnek alker. Ülkemizdeki en büyük deprem hasarları kerpiç binalarda çatı ve binanın beraber hareket etmemesinden dolayı oluşur. Bu davranışa rigid diyafram davranışı diye. Rigid diyafram davranışı olmayan yapılarda bu tip hasarlar çok fazladır. Kerpiç tuğlaların mekanik özelliklerine gelecek olursak, kerpiçin içinde toprak, su ve saman bulunmaktadır. Toprağın yeterli kil miktarının olması gerekmektedir. Suyun ise temiz, tuzsuz ve yağsız olması gerekmektedir. Samansa ne çok taze ve ne de çok uzun olmalıdır. En etkili olduğu an kısa ve üzerinden belli bir zaman geçmiş olan samandır. Aynı zamanda samanın ayrılarak karışımın içine koyulması gerekmektedir. Tabii su miktarı arttırılırsa çok iyi bir kıvam elde edilir kerpiç harcında, fakat bu istenmeyen çatlaklara sebebiyet verir. Çok az su miktarı ise kerpiç harcının istenilen şekle getirilmemesine sebep olur. Deprem etkisi altında kerpiç bir duvarda oluşan etkilere bakacak olursak, üzerinde bir kayma gerilimleri meydana gelebilir. İlk şekilde görüldüğü, sonuçta görüldüğü gibi. Veyahut diğer yönde eğer bir deprem etkisi olursa eğilme etkileri meydana gelir. İki kerpiç duvar birleştiği anda yine bir kayma gerilimleri meydana gelebilir şekilde görüldüğü gibi. D ve E şıklarında, alttaki şekillerde ise farklı en boy oranlarında sahip kerpiç duvarlarda oluşan çatlakları görmektesiniz. Minimum basınç gerilmesi 1 Newton bölü milimetre kare, minimum çekme gerilmesi de kerpiç bir duvar için 0,5 Newton bölü milimetre kare kabul edilebilir. Kerpiç binalardaki temellere bakacak olursak, oturmalardan kaçınılmalıdır kerpiç binalarda. O sebeple sıkılaştırılmış zemin kullanılmalıdır. Kerpiç binalardaki temel yüksekliği zemin koşuluna bağlı olarak seçilmelidir. Temel taştan veya pişirilmiş tuğladan yapılmalıdır. Yüksek su seviyesinden kaçınılmalıdır. Çatılara bakacak olursak, çatılarda uniform bir yük dağılımı olmalıdır. Yani düzgün yayılı. Çatı malzemesi ahşap, makas veyahut betonarme döşeme olmalıdır. Türkiye'deki en büyük deprem hasarları çatılardaki hasarlardan meydana gelir. Bunun sebebi de daha önce de bahsettiğimiz gibi çatılarda kullanılan çok büyük kütükler ve aynı zamanda çatının binayla bağlantısının olmamasından kaynaklı hasarlar meydana gelir. Kerpiç bir binada basit bir deprem güvenliğini incelemek istersek, simetrik 10 metreye 10 metre toplam taban alanı 100 metrekare olan tek katlı bir bina kabul ettik. Bu binada 6 tane kapı açıklığı, 9 tane de pencere açıklığı bulunsun. Boyutları görüldüğü gibidir. Bütün duvar kalınlıklarının kalınlığı 0.40 metre alındı. Kat yüksekliği ise 2.70 metre. Kerpiç duvarlarının birim hacim ağırlığı da 20 kN/m3 olarak alındı. Burada tabii bu değerlerin hepsi yönetmeliklerdeki ve çalışmalardan alınmış değerlerdir. Yaklaşık olsun diye. 1998 deprem yönetmeliğinde şöyle bir madde var. Pencere ve kapı açıklıkları haricinde tek bir yöndeki duvar uzunluğunun bina taban alanına bölünmesinin minimum değeri 0.25 metre bölü metrekare olmalıdır. Bu kural kullanılarak tek bir yöndeki duvar uzunlukları binanın taban alanına çarpıldığı zaman 25 metre olarak bulunur. İki yöndeki hem X hem de Y'deki toplam duvar uzunluğu ise 50 metre olarak bulunur. Tabi buna pencere ve kapı açıklığı dahil değildir. Toplam duvar alanları ise duvar kalınlığı çarparak 20 metrekare olarak bulunabilir. Duvar ve pencere açıklıkları ise sayıları ve uzunlukları çarpılarak bulunabilir. O da 21.60 metre olarak bulunmuştur. Duvar uzunlukları ve açıklık, kapı ve pencere açıklıklarının uzunlukları toplanırsa toplamda 71.60 metre bir uzunluk elde edildi. Ve sonuç olarak duvarlardaki düşey yükler şu şekilde hesaplanabilir. Toplam uzunluklar çarpı kat yüksekliği eksi kapılardaki kapı sayısı çarpı kapının alanı eksi pencere sayısı çarpı pencerenin alanı çarpı 0.40 metre duvar kalınlığı çarpı 20 kN/m3'te kerpiçin birim hacim ağırlığı. Toplamda duvarlardaki yükler 1368 kN olarak bulunmuştur. Biz bu binaya aynı zamanda bir çatı yapmak istediğimiz zaman betonarme plaktan bir çatı düşündük. Bu betonarme plağın kalınlığı 0.10 metre ve birim hacim ağırlığı 25 kN/m3 olsun diye düşündük. Termal izolasyonu sağlaması için bir kil tabaka olabilir. Onun da kalınlığı 0.15 metre ve birim hacim ağırlığı 20 kN/m3 olarak düşünüldü. Kaplama yükü bir çatıda düşünüldü ve bu da 1 kN/m3 olarak alındı. Bina planıyla çatı planı aynı düşünülerek çatının alanı da bir 100 metrekare olarak alındı. Ve sonucunda çatıdaki yükler de 0.10 metre çarpı 25 betonarme plaktan gelen, 0.15 çarpı 20 kil tabakadan gelen ve 1 kN/m3'de ek yük olarak düşünüldü. Bu çatı alanı ile çarpıldığı zaman çatı yükü 650 kN olarak bulunmuş oldu. Ve toplam bina yükü ise duvarların yüküyle çatı yükünün toplamından 2018 kN olarak alındı. Binaya gelen deprem kuvvetini bulmak istersek Türkiye Bina Deprem Yönetmeliğinde verilen spektrum kullanıldı. Binamız hem kerpiç hem de tek katlı olduğu için çok küçük bir periyoda sahip. O sebeple Türkiye Bina Deprem Yönetmeliğinde spektrumda birinci bölgededir. O da 0.4 SDS ile SDS arasında bir ivme değerine sahiptir. Eğer SDS 1.22 kabul edilirse bu bölgede yatay elastik ivme değeri de G kadardır. Deprem yükü azaltma katsayısı seçilmemiştir ve R eşittir 1 olarak hesaba devam edilmiştir. Binaya gelen yatay deprem kuvveti bina yükü çarpı ivme bölü deprem yükü azaltma katsayısından bina ağırlığına eşit çıkmıştır. O da 2018 kilonewton'dur. Tabii bu deprem yükünden ve düşey yükten dolayı oluşan gerilmelere bakalım. Güvenle taşıyabilecek binadaki basınç gerilmesi 1 ve kayma gerilmesi 0.15 Nm/mm alınmıştır. Kayma gerilmesi çekme gerilmesiyle birbirine eşit olarak alınmıştır binada. Yaklaşık olarak tabii ki. Düşey yüklerden dolayı oluşan gerilmeler şu şekilde bulunur. Binaya gelen düşey yük olan bina ağırlığı bölü duvarların alanı ve iki yöndeki duvarlar alınmıştır. Burada 0.40 metre bina duvar kalınlığı çarpı 25 çarpı 2'de duvarların uzunluğu şeklinde ve buradan 0.10 Nm/m3 bulunmuştur. Bunun birden küçük olduğu görülmektedir. Düşey yüklere karşı dayanıklı diyebiliriz binamız için. Kayma gerilmesini bulmak için deprem yükü kullanıldı ve burada sadece tek bir deprem yönündeki duvarlar dikkate alındığı için tek bir yöndeki duvarların uzunluğu dikkate alındı. Taban kesme kuvveti, deprem kuvveti bölü duvar kalınlığı çarpı 25 metre tek yöndeki duvarların uzunluğu. O da 0.20 Newton bölü milimetre kare olarak bulunmuştur. Biz bu bulduğumuz kayma gerilmesini kontrol edebilmek için soruda bize 0.15 düz kayma gerilmesi verilmişti. Fakat şu anda yönetmeliğimizde de olan yığma binalarda düşey yükten dolayı da kayma gerilmesi kapasitesi arttırılması gerekir bir miktar düşey yükle beraber. Biz o katsayıyı 0.5 kabul ettik ve 0.15 artı 0.10 çarpı 0.5 0.20 Newton bölü milimetre kare oldu. Görüldüğü gibi talep ve kapasite birbirine eşit çıktı. Tam sınır durumundayız. Fakat şöyle bir durum var tabii ki. Bizim hesaba katmadığımız pozitif durumlar var. Seismic yani deprem kuvvetine karşı daha hesaba katmadığımız şu ilk 3 madde var. Onlar da şu şekildedir. Sadece duvarlar değil, tek bir yöndeki duvarlar değil, duvarların köşeleri de aslında deprem kuvvetine karşı koymakta. Biz bunları hesaba katmadık. Deprem yükü azaltma katsayısını 1 aldık fakat bu daha büyük alınabilir. Ve aynı zamanda kayma gerilmesiyle çekme gerilmesinin birbirine eşit olduğunu soruda söylemiştik. Kayma gerilmesi veya çekme gerilmesi 0.15 minimum olduğunda bu daha 0.40'a kadar arttırılabilir. Son olarak yeni Türkiye Bina Deprem Yönetmeliği için kerpiç binaların önerip deprem kuralları da şu şekilde sıralanabilir bu bölümde. Biz bu bölümde yeni yapılacak kerpiç binaların deprem yükleri altında ve düşey yükleri altındaki kurallarını verdik. Bunlar aynı zamanda mevcut kerpiç yapılar içinde kullanılabilecek kurallar. Kerpiç tuğlaların boyutları TS 2514 ve 2515'e göre alındı. Bunlar kuzu ve ana diye. Kuzu küçük tuğla, ana da büyük tuğla olmak üzere tablodaki gibi. Aynı zamanda taşıyıcı iç duvarlar 1, taşıyıcı dış duvarlar da 1,5 kerpiç tuğla boyunda olmalıdır. Bina kullanım sınıfı ve bina önem katsayısı Türkiye Bina Deprem Yönetmeliği ile aynı alınmıştır ve 1 değeri alınmıştır. Eğer bodrum yapılacaksa bunun taşla olması gerekmektedir. Kısmi bodruma izin verilmemektedir. Bodrum katın en büyük kat yüksekliği 2.40 metre, normal kat yüksekliği ise en fazla 2.70 metre olabilir. Mümkün olduğunca dikdörtgene yakın ve simetrik bir kat planı seçilmelidir. Konsollara izin verilmemektedir. Bizim binamızın zeminle kerpiç duvarlar arasında en azından 0.50 metre yüksekliğinde bir taştan bir zemin yapılmalıdır. İlk numarik analizde söylediğimiz gibi pencere ve kapı boşlukları haricinde tek bir yöndeki duvar uzunluğunun bina kat alanına oranı 0.25 metre bölü metrekare alınmalıdır. En büyük açıklık değeri 4.5 metre alınmalıdır. Burada da bütün söylediğimiz kurallar tek bir şekil üzerinde gösterdik. Tabi buraya ek olarak bir de pencere ve kapı boşlukları da bu şekilde görülmektedir. Daha ayrıntılı bilgi için bildiriye bakılabilir. Lentolara bakılacak olursak kapı ve pencere üstlerinde uygulanmaktadır ve en küçük kesitleri 0.10 metreye 0.10 metre olmalıdır ve bu lentolar en azından 0.20 metre kadar uzatılmalıdır. Hatıllara bakılacak olursa bu hatılar iki tiptir. Bir tanesi betonarme hatılar. En azından bir hatılın kalınlığı duvar kalınlığı kadar olmalıdır. 0.20 metre yüksekliğe sahip olmalıdır. En küçük beton kalitesi C16 olmalıdır. En minimum enine donatı Fi8 250, boyuna donatı ise en azından 6 Fi10 olmalıdır. Eğer hatılarımız ahşap olacaksa en azından 0.10 metre bir kesite sahip olmalıdır. Aynı zamanda hatılarla lentoların birleşmesi gerekmektedir. Hatılar aynı zamanda çatıyla da bağlantıyı sağlayacak şekilde olmalıdır. Eğer biz çatımızı betonarme plaka 0.10 metre kalınlığında yapıyorsak hatılarımız da en azından bunu karşılayacak şekilde 0.20 metre yüksekliğe sahip olmalıdır. Burada da şuradaki kerpiç duvarlarla çatı arasındaki bağlantıları görmektesiniz. Temellere bakılacak olursak temel kalınlığımız eğer bodrum katımız yoksa en azından 0.50 metre olmalıdır. Eğer bodrum varsa bu değer 0.60 metre kadar olabilir. Temel derinliği ise 0.80 metre olmalıdır. Temeldeki duvarlar ve bodrum temeldeki duvarlar en azından 0.50 metre kadar devam ettirilmelidir yüzeyden. Bir de temellerde ve bodrum katlardaki kullanılacak taşlar çimento harçlı taşlar olmalıdır. Çatılara bakacak olursak ahşaptan veya betonlama plakadan yapılmalıdır. Eğer duvarlarla çatılar arasındaki bağlantı yeterli ise termal izolasyon için kil tabaka koyulabilir. Eğer kil tabaka koyuluyorsa en fazla 0,15 metre yüksekliğinde olmalıdır. Çatımız olabildiğince hafif olmalıdır. Çatı saçaklarıyla duvarlar arasındaki mesafe en fazla 0,5 metre olabilir. Şekilde de görüldüğü gibi. Sonuç olarak Türkiye'de çok fazla kerpiç yapı bulunmaktadır. Ama bunlar teknik doküman veya teknik eleman olmadığı için depremde yıkılmaktadır. Ve bu sonuç Türkiye Bina Deprem Yönetmeliği 2018'e yansımıştır. Bu çalışmayla beraber de Türkiye Bina Deprem Yönetmeliği'nin yenilenmesinde kerpiç binaların dahil edilmesi için kurallar verilmektedir. Teşekkür ederim.
Evet, biz teşekkür ederiz. Thank you very much for this interesting presentation about earthquake resistance and their application in Turkey. We have one question, but we will have the question round at the end of this session. So we kindly ask our presenters to join the discussion round at the end of this session. We will continue with the next presentation by Alper, İLKİ. The co-authors of the paper were DEMİR and Mehmet Cemal Genes. Mehmet Cemal Genes from the Eastern Mediterranean University. DEMİR and Alper İLKİ are from Istanbul Technical University. The topic of their paper is Seismic Design of Masonry Buildings in TBEC 2018. And Alper İLKİ will present now the paper.
Hello, Mr. ŞİMŞEK. Hello, everybody. I don't know, should I speak in Turkish or English? I just could watch the previous speaker, which was in Turkish. So what is the preference? Should I speak in Turkish or English? Is there a preference? I don't know.
I think English would be better because there are also guests from abroad.
Okay.
So
okay, thank you. So I will try to briefly summarize the issues in new seismic design code, basically Turkish Building Earthquake Code 2018 on masonry buildings. Unfortunately, as the previous speaker rightly mentioned, that due to poor performance of KERPİC buildings, Adobe buildings, we had to kind of remove this kind of construction from the code, which we are not happy to do that. But since we didn't have at that time sufficient research on kind of better behavior of KERPİC buildings, there was no chance for us. Not only KERPİC buildings, but also other unreinforced masonry building construction is limited to very few occasions, not very high seismicity and not very high in terms of stories. So it's maybe some other presenters may have shown this slide that we know that masonry buildings is our old friend, constructed for many years. And in Turkey, we have many high-rise, I could say high-rise because we have Galata Tower, also we have Beyoğlu Devlet Hastanesi, like 11-story high buildings.
Hocam affedersiniz, tam ekran yapabilir miyiz acaba?
Bakayım. Olmadı değil mi daha?
Sunum moduna
Evet,
geçelim
hocam. Evet. Evet. Şimdi daha iyi mi bilmiyorum.
Thank you very much. Yes.
Okay, thank you. So yeah, we have high-rise masonry buildings in Istanbul and in some other parts of Turkey, as well as many mosques and minarets. So it's a kind of common type of structure in Turkey. The problem is we have a large variety of materials, sometimes good, sometimes bad. Sometimes non-structural bricks are used as structural members, which end up with collapse or heavy damages during the earthquakes, which of course makes people approach this kind of construction more carefully. So until 2018, we had only allowable stress design method in Turkish seismic design codes. And when we modified the code, 2007 code, ultimate strength design was one of the main revisions on masonry part. And I could say that based on USTEP, the planning of the state about the earthquake resistance overall the country, we were recommended to follow European codes basically. So the Eurocode 6 and Eurocode 8, masonry and seismic design part of Eurocodes were the basis of the revisions. Of course, the issue is that these codes will be revised in future, so probably we will be adapted to these changes as well. So what's new in Turkish Building Earthquake Code 2018? Basically, as I mentioned, we are now using ultimate strength method, which is a big change for this masonry design. And also equally important, there are new masonry types on top of unreinforced masonry, which was the only covered masonry type in the previous code. So now we have confined masonry, we have reinforced masonry, and also we have reinforced panel buildings. And I could say that while confined masonry and reinforced masonry are common in many parts of the world, reinforced panel AAC buildings, this is a lightweight concrete buildings, I could say, is, as far as I know, the first time codified, and that's codified in Turkey through a research with a combination of different universities and relevant associations. I will show some of those, and I believe I have many slides, but probably just I will be able to introduce these different types of new masonry systems to the audience because of probably lack of time and because probably I could not make a good organization of the presentation, and sorry for that. So unfortunately, as I mentioned, although there are new design approaches and new masonry types, the code had to restrict use of Adobe and some other materials due to the non-standard material quality and also the workmanship and the resulting poor performance during the previous earthquakes, not only in Turkey, but also other countries. Of course, we have good examples too, but the non-standard quality made these kind of restrictions valid in the new code. So we hope to make some more research. We have to improve, as the previous speaker, the seismic performance of the earthen materials and structures so that we can somehow make them better behave during the earthquakes. Unreinforced buildings, there are rules for that in the seismic design code, which are well known to everybody. So I'm not going to spend some time and passing the confined masonry buildings, which is kind of new in Turkey in terms of seismic design codes. Actually, we had such structures. As you see, the structure on the right-hand side is a kind of confined masonry. We have a lot of these buildings in all steels, where first the walls are constructed and then the concrete members, which are kind of weak columns, weak beams, like tie beams, are constructed afterwards. Now this is codified and there are rules, construction rules and detailing rules in Turkish seismic design codes, and we call it kuşatılmış yığma in Turkish, the confined masonry. And reinforced masonry is even a better application with higher ductility, and the code allows significantly high buildings to be constructed using this kind of technique. Of course, while we do that, we were always in contact with the industry, with the brick industry and those other people, and we asked the possibility of producing such kind of members, and they were very willing to do that, and they were happy to do that because, you know, the masonry construction is getting less and less day by day. So they need to have a new kind of opening, new frontiers in front of them. So they were very willing to apply this kind of new materials in their production. So here you see the reinforced masonry buildings where we have longitudinal bars as well as horizontal bars along the horizontal joints. So much more ductile behavior we have with these kind of masonry systems. And as you know, the reinforced masonry is not a new actually technique. In traditional construction, we have a lot of reinforced masonry structures like you see here, or sometimes we kind of use wood as kind of reinforcement, and that's one of the interesting photographs, masonry to reinforce concrete building on the same area. So they perform well if detailed and designed properly. And this one is new, as I mentioned. While this is used all around the world, including Turkey, it was not codified. So up to this code, the regulations about how to design those, how to calculate those kind of structures are now in the code. Basically, we have a reinforced panel like that, used either as walls or slabs. And in between them, we have reinforcing bars, both in vertical and also horizontal directions. And these are connected to the foundation and the beams, I could say tie beams, around the structure. So you can build some like 2-story, 3-story buildings using this technique. And since it's produced in the factory, the quality is more promising and more standard. These kind of buildings have been constructed in the past, like more than 5,000 buildings, mostly right after the earthquakes. They were constructed rapidly and used as a kind of shelter houses right after the earthquakes. And also there are different types of building, one of which is in Gölcük. We have examined this after the earthquake and analyzed it in detail. So that it really performs well, also as demonstrated after the earthquake. So maximum heights are given here. I don't want to spend some time, just you may have a look, but as you see, we can go up to 17.5 story, which is like maybe 6-story building using particular reinforced masonry or using the panel buildings. And also you can build quite high structures with respect to previous limitations of masonry buildings in 2007 code. Yeah, about different units, you can use bricks, etc., the AAC, natural stone, and artificial stones, but unfortunately, some other materials are prohibited in this code. And there are different definitions based on the type, based on the void ratios, but I'm not going to spend some time. These affect the material characteristic strengths and design strengths that we have to take into account during design. And I'm passing these slides. If you have any question, I will try to answer. These are showing how we determine the characteristics of the materials in compression, in shear. Like previous speaker also has mentioned, we have now, as I said, ultimate strength design methodology approach, where we have partial material safety factors, unlike a low stress methodology. And here the material factors are for all materials or masonry blocks, it's 2. For steel bars, it is 1.15. And for factory produced aerated concrete metal, it's 1.75. And these are given for the elastic modulus as well as shear modulus of masonry. In case of structural analysis, now we kind of want to force engineers to model the structure using finite element modeling and analyze the structure under vertical and horizontal laws rather than simple hand calculations. There was a chapter, simplified chapter, but it is then removed after discussions from the code. Either finite element analysis or equivalent frame analysis methods are allowed. And like concrete structures, it's also new for concrete structures. Effective stiffness are being used in 2018 code. This is valid for masonry structures as well, considering the possible cracking during the earthquakes. And again, a new concept for masonry structures. Now we consider ductility with seismic load reduction factors up to 4 for reinforced masonry and reinforced AAC panels, and 3 and 2.5 for other types of masonry, as well as for shear and for brittle failure mechanisms. We have overstrength factor, which should be taken into account during design. And drift limits are broad, and it's 0.7% under the seismic loads. Rigid diaphragms should be provided somehow. This should be proved in the analysis, of course. That's one of the main problems we experienced after the earthquakes. Many damages are occurring because of lack of sufficient diaphragm on the structure. Therefore, the structure doesn't behave like a box. About out-of-plane failure mechanism, no regulations are put in the new code, but there are some indirect limitations which will avoid out-of-plane failure mechanisms. And the code allows to go beyond these limits, provided that some additional calculations has being carried out based on Eurocode. But since we have only limited amount of pages, we could not go into much more details. So I'm passing these because of the limits of the time. As I said, the walls are designed like columns or shear walls, considering the reinforcement inside using basic mechanics of basically reinforced concrete design. The panels are considered again like reinforced concrete walls, but they are considered separately because during the earthquakes they are separated from each other. Both unreinforced masonry and reinforced masonry structures are designed considering diagonal tension failures, diagonal compression failures, as well as shear slip behavior. All the equations are given, so the walls should satisfy all of those. So I know just 1 minute or something like that, I guess, just to summarize some damages experienced during the earthquakes. The diaphragm is one of the main problems. Poor connections of the walls in different directions, as well as the connections of different layers of the walls in transverse direction are among main problems. Out of plane failures are also commonly observed. And this is, of course, you see one story was lost here. This is in Elazığ, the previous earthquake, in 2010 earthquake. One story has been lost because simply they haven't used proper bricks, and also the walls were poorly constructed. In Palu, there were a lot of KERPİC buildings which performed extremely well, provided that these kind of wooden tie beams were used in the structure. You see, these are two-story structures, sometimes more. Most of them have been performed exceptionally well in Palu earthquake. So yeah, I talked most of them, so I'm passing these slides not to take much of your time. Yep. There are many non-engineered confined masonry buildings all around Turkey. As you see, this shows how confined masonry is done. There are places left for vertical members, concrete members. They are cast after the wall is constructed. And yeah, finally, what I would say is there are new, as I mentioned, there are new methodologies, new types of masonry construction allowed in Turkish Seismic Design Code, and we hope to improve and apply more widespread KERPİC as well. And I think we have to study, we have to research on the better seismic performance of these kind of structures. My previous colleague have made some suggestions. I believe they should be verified with some more research, some more maybe testing. So with that, I complete my presentation, and thanks a lot.
Thank you very much, Alper Tilki, for this very interesting presentation. We will maybe have questions at the end of the session.
Sorry, but there is a graduation project meeting that I have to leave. Okay. So if there is some questions, I will please to answer now, if possible.
Hocam yapabiliriz. İlk iki konuşma zaten birbiriyle ilgili. Bu ilk iki için soruları alalım. Sonra Alper hocamızı da uğurlamış oluruz.
Tamam, çok iyi olur Ömer hocam.
Okay, if this is possible, then I would like to ask the first question, which we had after the first presentation. Actually, one question to Muhammed Şükrü YAVAŞ was from Hasan Mert Uğur. How can we build earthquake-resistant Adobe buildings? Depreme dayanıklı kerpiç yapıları nasıl yapabiliriz diye böyle bir sorumuz var.
Biz zaten onu açıklamaya çalıştık. Okursa daha faydalı olur yani bizim yazımızı. Oradan öğrenebilir. Yani dediğimiz gibi en büyük hasarlar çatılarda oluşuyor, kerpiç yapılarda. Kerpiç yapının kendisiyle çatı beraber çalışmadığı için bunlarla alakalı önlemler almak gerekiyor. Onun dışında temellerle alakalı problemler oluyor. Belli önlemlerle kerpiç yapılar depreme dayanıklı yapılabilir.
Yes, as you mentioned, we had now 2 presentations about this topic with a lot of informations.
I have a question to Albert, please.
Excuse me, if there are some more information needed, our presenter asks you kindly to look into the paper where everything is explained in detail. We have a second question to our second presenter. It says, can reinforced concrete be used in foundations and basement walls against earthquake loads?
For Adobe buildings, right?
I guess it's not mentioned in the question.
Yeah, probably questions like that. Yes, I think it's a good idea. And also previous speaker, Şükrü, has also mentioned about the kind of use of a better material like stone in the basements. Of course, like stone, we can easily use reinforced concrete shear walls, etc. But of course, then the question comes, why we use at the top another kind of material, which can be explained with kind of reflecting the tradition and making use of better characteristics of in terms of insulation and architecture, etc. Of course, the answer is yes. We can use reinforced concrete foundation as well as the basement walls. Correct.
Yeah, I have a question.
I don't have any other questions from the chat, but we can ask here in the our Zoom display and discussion. Yes.
Okay, Dr. Alper, thank you so much for your
My
presentation. It was wonderful, really. I have just two questions.
Sure.
The first one regarding the tie beam. You showed us that in Bolu buildings, they are putting a tie beam of wooden tie beam, and you mentioned that this tool would be successful. And early in the morning, we saw Dr. Bilgi, and she presented a type of mesh, plastic mesh, inserted within the courses. Okay, so what do you think about this mesh material?
Horizontal layer.
Yeah, of course, that's a very good idea for new Adobe buildings, so that the tensile strength is increased significantly, as well as ductility is increased significantly. The mesh will help to get not only the tension forces, but also it will allow larger displacement, larger deformations along the wall. So of course that's a very good idea, and actually it's a kind of reinforced masonry, as you mentioned, like the woods or different types of reinforcement. Of course, that's a good application.
Yeah, my second question is regarding the new techniques for using earth as a building material, especially if we are regarding the compressed earth block and rammed earth techniques. You mentioned that there is no any cause or research covering the Adobe. Adobe, we know, Adobe, it is a traditional way of using earth in construction. But what about the modern techniques? What about the modern materials, which is fully covered with researches determining its property? Are there anything regarding these new materials?
Unfortunately, in Turkey, into my best knowledge, or not personally my knowledge, but all the masonry committee, we didn't find a sufficient amount of research carried out in Turkey. But I should confess that we didn't have much time to consider the research all around the world. If we could have some chance to do that, maybe we could have chance to include Adobe in the new code as well. What I should say, Doctor, actually, even the masonry part, I mean, nobody is very much caring about masonry part. I mean, it is like nobody is interested in masonry. So even as a code writer, you sometimes are desperate. I mean, why I am writing this while nobody cares about masonry? And unfortunately, Adobe is even the less part people doesn't give importance. So that was probably why we didn't have some chance. So we need support of those people who made some solid research, some real ideas to be applicable to codes, not only tests. I mean, if you make a test, if you can show that's behaving good, that's not unfortunately enough. We should put forward some design rules, design details, which will be valid, which will cover all cases. So I think we had lack of such kind of information while we were preparing the code. But we are open to any support in that aspect.
Yeah, I totally agree with you. Yeah, thank you so much.
Thank you. My pleasure.
Thank you very much, Alper, İlki. Are there other questions?
Benim bir sorum var. Duyuluyor mu?
Duyuyoruz hocam.
Evet, Bilge hocam. Yes.
Tamam, şöyle. Şimdi inşaat mühendisleriyle mimarlar biraz farklı yaklaşıyorlar konuya. Betonarme sistemlerde donatı maksimum çekme kuvvetlerinin olduğu yerde. Yani kiriş dersek en alt uçta, kolon dersek en dışta. Şimdi yığma yapıya geldiği zaman donatı niye merkeze konuyor?
Yani aslında bana mı sordunuz hocam? Bana sorduysanız.
Alper İlki.
Okey. Ve Türkçe sorduğunuz için Türkçe cevaplamaya çalışacağım. Hocam aslında yani merkeze koymuyoruz. Yani şöyle, yığma yapıda yani bunu bir betonarme perde gibi düşünürseniz aslında betonarme perdede de gene aynı şekilde düşeyde ve yatayda bütün perde gövdesine bu donatıyı koyuyoruz. Esasında imkan olsa confined masonry gibi, kuşatılmış masonry gibi uçları da koymayı tercih ederiz. Ama ikisini birleştirmedik yönetmelikte. Yani ya confined masonry dedik, sadece uçtaki atıların olduğu yer donatılandı. Ya da bütün gövdeye yatay ve düşey donatıları koyduğumuz donatılı yığmayı önerdik. Ama donatılı yığmada da gene özellikle köşelerde söylediğiniz gibi kiriş alt ve üst ucu gibi daha yoğun donatımız var. Dolayısıyla aslında söylediğiniz gene geçerli. Yani ortada gibi gözükse de betonarme duvarlardakine benzer bir donatı düzeni var. Tabii duvar boşluğunun vesairenin imkan verdiği ölçüde bu boşluk, bu donatılar var.
Peki sen muhtemelen sabahki benim konuşmamı dinleyememişsin.
Hocam 5 ders vardı maalesef. Dersler bitti, buna ancak koşabildim.
O zaman bir cümleyle onu hatırlatmaya çalışacağım diğer dinleyicilere. Benim Avustralya'da test yapılan sarsma tablosu üzerindeki duvarda bambularla dışta. Şimdi sana söylediğimde donatı yığma duvarın merkezine konuyor demiştim. Bu çok uygulandığı görülen bir sistem. Onun dışında Avustralya'da bambudan donatılandırma kerpiç duvarda dış tarafa koyuyorlar ve dış tarafa koyduğunda ikisini birbirine duvarın kesitinin içinden bağlıyorlar. Her nereden bağlandıysa kuvvet uygulandığında o noktadan kırılıyor. Yani burada neyi söylüyorum? Tekil donatılandırma dışta da yapılsa faydası yok, eksende de yapılsa faydası yok. Üçüncü örnekte Almanya'da sarsma tablasında yığma duvarın yüzeyleri donatılandırılıyor ve onlar harçla giydirilmiş oluyor. Ama sarsıldıktan sonra esas taşıyıcı olan yığma duvar salladığınız zaman içerideki yığma duvar paraladığı için dışarıdaki yüzey donatıları da paralanmış oluyor. Sonuç olarak da benim burada anlatmaya çalıştığım yatay kuvvetlerde aşağıdan yukarıya doğru enerji söndürme yüzeyleri olduğu takdirde bir bina 2,5 metre yüksekliğinde diyelim 50'şer santim arayla kaydırma düzlemi, enerji söndürme düzlemi koyduğumuz takdirde 4 defa tekrarlıyoruz demektir. 4 defa tekrarladığımızda yanala gelen yük 4'e bölünmüş oluyor. Ve dolayısıyla etkisi sadece ince bir çatlak yapıyor. İnce bir çatlak yaptığında yatayda olan çatlak yığma duvarın taşıyıcılığıyla hiçbir rahatsızlık meydana getirmiyor. Yani bunu burada tekrardan vurgulamaya çalıştım ki inşaat mühendisleri habire donatılandırmaya çalışıyorlar. Halbuki kırıldığı yeri kontrol ettiğimiz yerden kırılırsa yapı taşımaya devam ediyor. Teşekkür ederim.
Ben teşekkür ederim hocam.
Thank you very much, Professor Bilge Işık, for this explanation. We will continue.
Hocam,
evet.
Bitirmeden bir şey de ben sorayım. Alper hocam hazır buradayken onu göndermeden. Hocam.
Görmüyorum, Muhammed mi?
Efendim?
Hocam.
Ömer Dabanlı
Benim.
is asking the question.
Hocam çok teşekkür ederiz katılımınız ve katkınız için öncelikle.
Estağfurullah.
Şimdi aslında tabii Türk yönetmeliğinden bahsettik ama İngilizce'de olunca sanki İngilizce bilmeyenler için de biraz böyle mesajı da tam verememiş gibi olduk. Ben açıkçası şöyle genel ana fikrini kısaca özetlemeniz mümkün olabilir mi? Faydalı olmak açısından diye sizden rica edecektim.
Çok teşekkürler Ömer Hoca bu fırsatı verdiğin için. Ana fikir şu. Özellikle bu konferansın konusuyla alakalı olan KERPİC ile ilgili. KERPİC'i biz kullanmak istememize rağmen ben de tarihi yapılarla ilgili Ömer Hoca ile diğer hocalarımızla da beraber pek çok yapıda da çalışıyoruz ve hani gönlümüzde KERPİC'i de kullanma niyeti var. Fakat maalesef yığma yapılar bırakın KERPİC'i, tuğla veya başka türlü yığma yapılar bile hani yönetmelikte böyle en az ilgi gören, kimsenin böyle pek çalışmak istemediği, artık yığma mı kaldı, bundan sonra yığma mı inşa edilecek gözüyle baktığı, yazalım mı yazmayalım mı diye düşündüğümüz bir bölüm. Şimdi özellikle de KERPİC iyice tabii yapımı azalan ve bir çaba gösterdiğiniz zaman da uygulamaya ne kadar geçeceğine emin olamadığımız bölüm olduğu için yönetmeliğe koyamadık. Ve maalesef daha önceki depremlerde gördüğümüz standart olmayan imalat ve malzeme, uygulama ve detay hataları sebebiyle de gördüğümüz kötü performanslar sebebiyle burada bonkör davranamadık. Sadece KERPİC için değil, bu donatısız yığma için de. Bütün bunların kullanımını sınırladık eskiye göre ve daha yeni, daha modern yığma tekniklerini yeni yönetmeliğe entegre ettik. Bunu yaparken biraz da Eurocode'daki malzeme türlerini ve yapı türlerini de ortaya koyduk. Çünkü bu devletin genel deprem yönetmeliği yönlendirmesi de bu vardı. Eurocode'la uyumlu bunların olması gerekiyordu. Bununla beraber şuna bütün kalbine katılıyorum. Hem Muhammed Hoca'nın söylediği hem Bilgi Hoca'nın söylediği kerpiç yapıları da biz belli bazı detaylara dikkat ederek, belli bazı tekniklere dikkat ederek depreme dayanıklı yapabiliriz. Bilgi Hoca'nın bu yönde çabaları olduğunu biliyorum. Bir kısmından ben de destek olmuştum belki 15-20 yıl evvel bizim laboratuvarda. Ama bunların Doktor Muhammed'e de söylediğim gibi sadece deney yaptık, bu çıktıdan bir adım öteye gidip tasarım kurallarını ortaya koymamız gerekiyor hep beraber. Yani kerpiçe gönül veren buradaki bütün insanlar kendine dahil olarak bir araya gelip büyük bir araştırma projesi kapsamında sadece evet bak bunu koydum iyi çalışıyor, bunu koymadım kötü çalışıyordan öte bütün yapının tasarlanmasına imkan verecek birleşimi, temeli vesairesi bütün tasarım denklemlerini ortaya koyacak. Belki çok basitleştirilmiş, çok basit kurallar ortaya koyacak yöntemi üzerinde çalışıp koymamız gerekiyor. Kısaca kerpiç yönetmelikte şu anda yer almamakla beraber bunu birlikte çalışırsak yapabileceğimizi söylemek isterim. Yönetmelikte de onun dışında da bahsettiğimiz gibi donatılı yığma gibi, kuşatılmış yığma gibi ve gaz beton panellerden oluşan yığma yapılar gibi yeni yönetmelik kavramları ortaya kondu. Ve bunlarla beraber gene yeni yönetmelikteki yığma yapılar anlamındaki en önemli değişiklikte daha önceki emniyet gerilmeleri yöntemine göre hazırlanmış olan yönetmelik şu anda taşıma gücü kavramına geçildi. Bu sadece yığma yapılar için değil, temellerde ve zeminlerde de buna geçildi. Zeminler de eskiden taşıma gücüne göre değildi. Artık bütün zemin güvenliği taşıma gücüne göre ayarlanıyor, kontrol ediliyor. Bu anlamda en büyük yönetmelik değişiklikleri bunlardı. Bilmiyorum, zamana emin olamadığım için Ömer Hocam biraz acele konuştum ama başka daha spesifik bir şey varsa onu da cevaplamaya çalışacağım.
Hocam, yani konu önemli olduğu için vakit belki biraz alıyor ama peki şöyle şimdi meslektaşlarımız şikayet ediyorlar tabii işte kerpici biz yönetmelikte olmadığı için yapamıyoruz diye ve belki de idareden de bu noktada işte yönetmeliği nereye uyduracaklarını bilemedikleri için biz o zaman şöyle bir şey düşünülebilir mi? Yani yönetmelikteki yığma malzemelerinden birisi gibi tahayyül edilip o şartlara uyarlanarak kerpiç yapılabilir mi? Aslında benim aklımdaki en kritik soru bu.
Bu çok güzel bir soru. Bence oradaki mekanik özellikleri, boşluk oranı zaten olmayacak kerpiçte. Sağlamak kaydıyla bana göre bunun önüne yani bunu bir şekilde bypass etmiş olursunuz. Çünkü buradaki kaygılar bu özellikleri sağlayamaması. Bunun isminin tuğla olması veya kerpiç olması fark etmez. Bir, bu şekilde problem çözülebilir veya kullanımın önü açılabilir. İki, bütün yönetmeliklerde olduğu gibi bizim yönetmelikte de şunlar var. Bu yönetmelikte kapsanmayan konular dünyada geçerli işte deneylerle veya başka yönetmeliklerle depreme dayanıklı gösterilirse bunu kullanma şansımız ve hakkımız var. Bu da ikinci bir alternatif olabilir. Belki ikisi bir arada. Bu şekilde önü açılabilir diye düşünüyorum.
Ömer Hocam, the guests in the meeting ask to continue in English if it's possible.
Evet, onu anladık ama asıl bu Türk katılımcılara mesaj olsun diye özellikle istediğimiz bir şeydi.
Evet.
İngilizceyi özetlemiş oldu hocamız.
Evet, ben onu yazmıştım. We had now for our guests we had a short summary of Alper İlkİ's presentation. This is in Turkish. This is why we continued in Turkish. Ömer Hocam, if we have time, we have one more question in English.
Benim şu an sorum yok ama varsa alabiliriz.
We have one more in the chat from Senem Kahraman. What should be considered in Adobe wall connection of reinforced concrete or stone foundation against earthquake loads?
Basically, this will be provided. Soru bana diye ben girdim ama
Tabii,
herhalde
evet,
öyle.
Alper
Okay.
Hocam.
Basically,
Muhammed Yavaş.
the connection basically will be done through friction, whatever the masonry structures are. So, if we are building a typical Adobe structure without reinforcement, what we would be just have a roughened surface, and on that we would have the Adobe construction directly as is. This is done what type of masonry you do. I mean, whether it is stone and brick or other kinds of material. So I can't think of another connection. But of course, if we want to improve this behavior in the connection of concrete to Adobe, there can be some, like putting some anchorages, putting some different types of reinforcement between two materials. These are all possible. But I think, in fact, there is no need if the amounts of walls, thickness of walls are sufficient. So the friction could be enough in that connection.
Ben tekrar bir şey danışmak istiyorum veya söylemek istiyorum. Çok fazla çalıştım yama yapı üzerinde. Birinci konuşmamız yama yapının donatılandırılması hakkındaki görüşlerimi söylemiştim. Düşey donatılandırmanın tamamen hasar verdiği konusunda. İkinci konu da kuşatılması idi. Kuşatılma, yatay ve düşey hatıl konulması. Değil mi?
Evet hocam. Evet.
Bu deprem yönetmeliğinde de var. Düşey hatıl koyuyor tam köşeye. Şimdi tam köşeye düşey hatıl konulmasını ben Dolmabahçe Sarayı'nda istiyorum. Dolmabahçe Sarayı'nın köşe duvarlarını kopartalım, oraya düşey hatıl koyalım. Nasıl?
Yani inşaat mühendislerine sorarsanız iyi olur derler hocam. Yani.
İnanılır gibi değil. İnanılır gibi değil.
Hocam tabii yani şimdi bunu imalat sırasında yaparsanız, yapsaydık bu dışarıdan bir görüntü olarak bir şey fark etmeyecekti biliyorsunuz. Ama köşe birleşimleri muhtemelen köşe birleşimleri...
Ağlanacak bir durum, çok özür dileyerekten. Köşe, yığma duvarı tam en taşıyıcı noktasıdır. Köşe olmazsa zaten yığma bina taşımaz. Ve tam o noktayı biz kopartıyoruz. Oraya birbiriyle bağdaşmayan, birbirine yük aktarmayan farklı bir malzemeden bir düşey hatıl. Düşey hatıl kolon değildir. Yani binanın yükünü taşımaz. Düşey hatıl ne olduğunu ben de bilmiyorum.
Amacı hocam neyse yani uzatmak istemiyorum. Yapıyı bir bütün olarak döşemeyle beraber, dört taraftaki duvarı beraber çalışmasını sağlamaya çalışan bir eleman diyelim ama şurada tabii haklısınız. Yani donatısız yığma bir yapı yapıyorsak ve o köşe birleşimlerini doğru yapıyorsak, duvar kalınlıkları yeterliyse, yukarıdaki diyafram çalışma bir şekilde sağlandıysa donatısız yığma olarak da depreme karşı iyi performans gösterebilir yapı. Düşey atılı olmasa da nitekim pek çok örneğini görüyoruz. Ama bildiğiniz gibi tersini de görüyoruz. O köşedeki uygulama o kadar iyi olmadığı zaman o köşelerdeki yığma duvarların yıkıldığında gene görüyoruz. O tabii belki düşey atıldan ziyade yatay atılla da sağlanabilir ama yatay atıl olmasına rağmen köşe duvarların yıkıldığını da görüyoruz çok kez. Hatta benim galiba bu sonuçta da vardı. Yatay atıl duruyor yerinde ama altındaki duvar yıkılmış durumda. Ama tabii yapıdan yapıya, deprem etkisinden deprem etkisine dikkatli düşünülmesi gereken konular diye düşünüyorum bunlar.
Peki, teşekkür ederiz.
Ben teşekkür ediyorum hocam.
Thank
Ömer
you
Hoca
very much.
teşekkürler fırsat için. My pleasure.
Okay, thank you very much. Ömer Hocam, should we continue with the presentations?
Yes, please.
Okay. Special thanks also to Alper, İLKİ, and Muhammed, Şükrü, YAVAŞ for the answers. We will continue with Asutan, Sarp, Yalçın from the Bursa Technical University with the presentation Acoustic Performance of Health Building Material Unfired Clay.
Yes, Asutan, Sarp, Yalçın, by the way. I'm sharing.
Asutan, Sarp. Oh.
Yeah, I'm sharing my screen. Okay, can you see?
Yes.
Okay. I'd like to start with introducing healthy buildings. The principal function of buildings is to present a healthy living environment by providing desired conditions to meet their users' needs. And healthy buildings fulfill biological, psychological, and sociological user needs by their quality indicators related to physical and social, outdoor and indoor environmental characteristics. And physical indoor environmental characteristics can be classified as dimensional, formal, visual, tactile, atmospheric, and auditory characteristics. Sound is a component of auditory characteristic, and it directly affects the performance, the comfort, and health of the users. Noise levels are measured in decibels in the range of 140 to 0 decibels, which are threshold of pain and threshold of hearing, and where 110 decibels shout into the ear, 90 for air traffic, 80s for road traffic, 50s for conversation, and 30s for whisper. And noise causes a wide variety of health problems, as we can see here. Adverse biological effects of noise on human health are hearing loss and sleep disturbance. As a result of noise disturbance and distress, psychological effects may arise as well. In connection with these psychological effects, social influences create negativity in users' relationships with others. And due to all these problems, noise causes stress formation in human body, and long-term exposure to it leads to stress-induced psychophysiological health problems. And this may occur in all systems of the body, as you can see here, but the affection of circulatory system can lead to serious impacts that may even result in mortality. Here, there are some examples of noise levels that may cause health problems. Earlier we said the most important issue was the cardiovascular disorders. So exposure to 50 decibel may lead to hypertension and myocardial infarction. So what should architects, what should we do? We should take some precautions of reducing noise levels to acceptable levels. How can we do that? The material selection of building elements is one of the most important issues to be considered during design. And unfired clay materials such as Adobe, rammed earth, ILKİ are, as we know, ecologically friendly because they require low energy input, they have high potential recyclability, and they are very healthy because they have excellent characteristics of relative humidity, temperature stabilization, condensation inhibition, odor absorption, fire resistance, electromagnetic shielding, and what about noise reduction? So the aim of my study is to reveal the acoustic performance within the scope of noise reduction and to find out whether unfired clay materials can provide a healthy indoor environment against noise. During the evaluation of acoustic performance of unfired materials, transmission and absorption should be taken into account as sound transmits through building elements, and after transmission, it may increase due to reflection. 95% of the sound energy is transmitted by mass vibration. How? At first, sound waves vibrate building elements, then the elements act like sound sources, and they emit sound by creating vibrations on the air of the receiver room. And building elements resist vibration by their masses. So the heavier the mass, the harder it is to vibrate. And this is called mass law, Berger's mass law. The mass per unit area of building elements can be calculated by this equation, which we multiply this mass per unit volume with thickness of the material. And here we can see the calculated examples to the masses of external and internal walls produced from several materials. Here, as we can see, our materials, unfired materials, are it's traditional Adobe incorporated with straw, rammed earth, ILKİ, are heavier when compared with other materials such as fired bricks, concrete, and gypsum, but except stone, of course. They're heavier because they're not hollowed, they have high density, and they are used with thick sections due to their load-bearing feature. And sound transmission loss determines the sound insulation property of building elements, and this STL increases with mass increase. So the heavier the partition, the less sound it transmits to the adjacent space. So to reach an acceptable sound level, the increase in mass can be achieved by increasing the thickness or selecting a building material, a building product with a high density. We can calculate the sound transmission loss, in other words, the sound insulation behavior, by this equation. It's a logarithmic value, as you can see. When we apply this equation to several materials, we can construct this table for external wall elements and internal wall elements. So sound transmission loss of wall sections obtained from unfired clay products here is compared with the other ones, and you can see the values of them, high values of them. Here the comparison has been limited with unplastered single leaf wall to be able to compare the properties of basic wall materials. And when we visualize that data, sound transmission loss of unfired clay products is higher than the other basic building materials except stone, as you can see here for external wall elements and here for internal wall elements, again except stone. And sound transmission varies with frequency, and frequency is the number of sound vibrations occurring in a unit of time, and it refers to whether the sound is treble, like a child voice, or a short string sound of an instrument, or its bass, for example, a man voice or contrabass sound, etc. As the frequency of the sound increases, sound transmission loss increases as well. And again, we can calculate the sound transmission loss at different frequencies by this equation. For 50 centimeter Adobe brick wall, I calculated like that, and to compare with other building materials, I applied the same calculation to the external and internal wall elements, as you can see here. And we can see from the figure that between 125 Hertz and 4000 Hertz, sound transmission losses of stone and unfired clay products are very close to each other, and they can be stated to be very good sound insulators. The values of solid fired bricks and concrete blocks are close to this group, and aerated concrete is the worst. For internal wall elements, the sound transmission loss of stone is the best, and followed by unfired clay products. The values of solid fabric and concrete blocks are close to this group. Hollow brick provide low sound insulation, but still better than aerated concrete and gypsum. Here at low, mid, or high frequencies, we can distinguish the difference in sound insulation of each building element, and it's easily readable from the figures that building elements have better sound insulation at high frequencies. We can see the 75 here. And I should also note that the linear graphic outcomes from calculations may not be obtained from measurement because at certain frequencies, lower sound transmission loss than calculated can occur. The reason for this is the decrease in the section's resistance to sound energy because of resonance and coincidence frequencies. So as a precaution, we can design an extra 5 decibel higher sound transmission loss values. And when we come to sound absorption, after transmission, sound is reflected by surfaces to a greater or lesser extent. It depends mainly on the absorption properties of building products, and it depends on the sound absorption coefficient. And this, the absorption is related to the porosity of the materials. So light materials with fibrous or open surfaces are good absorbers, but smooth hard surfaces are highly reflective to sound. And we can see some sound absorption coefficients of dense and solid materials here. As we can see, they are low, and these values, the data are in percentage. So our unfired clay materials, as we know, they are heavy, dense, and solid. So their sound absorption is fairly low. We should take additional precautions for it, such as decreasing the density by adding low dense materials into the clay mixture, such as basaltic pumice, or placing acoustic resonators within suitable locations, or laying bricks with gaps where load-bearing feature is not required. But we shouldn't forget that direct intervention to the unfired clay wall to improve sound absorption behavior will negatively affect the sound transmission loss, in other words, insulation properties. For the conclusion, with their average sound transmission losses of 54, 56 for external walls, 51, 53 for internal walls, unfired clay products are very good sound insulators. And with these values, they can easily reduce, for example, a highway noise of 80 to 90 decibels to the lowest acceptable noise levels in a building, ensuring sleep conditions of 35, 40 decibels. And for sound absorption, we should take precautions. It will be more appropriate to take precautions on the wall surface rather than its physical structure. As we said, changing the physical structure will negatively affect the sound transmission loss properties. So, in addition to its many excellent characteristics of environmental and health, unfired clay is a high performance material in terms of noise reduction, and the usage of this material in contemporary architecture will contribute to prevent noise-induced health problems before they occur and fulfill the basic requirement of users to lead a healthy life in a healthy building. Thank you very much.
Thank you to Asutan, Sarp, Yalçın for this very interesting presentation about the acoustic performance of unfired clay. We will continue with the next presentation, biological alterations in Adobe structures. The authors are Ayşe and Ayşe from Hatay Mustafa Kemal University and Murat Dal from Munzur University, and Ayşe will present now. Mikrofonu açık değil. Şimdi açıldı. Evet, yes.
Okay.
Okay. Hello, everybody. I know it's a little bit late time. Today, I'm going to talk about biological alterations in Adobe structures. As we know, historical buildings are the most valuable architectural works of our cultural heritage. Historical places were built of stone brick, mud brick, and wooden building materials. If traditional architectural structures are not protected properly, they are subjected to alterations in various dimensions. Damages caused by water and moisture and the most common causes of damage to Adobe structures for various reasons. The differences of historical buildings from modern buildings is that they are closer to the ground. Built with more porous materials, they collect water from the ground, carry it along their structure, and evacuate by evaporation, creating side effects such as oxidation and crumbling. Walls and floors are the point of change for these reactions. Increased soil moisture and a variable climate can lead to greater circulation of dissolved salts and hence damage to crystallization on decorated surfaces and also greater soil imbalance. Humans built their houses and monuments using soil in order to survive in the early days of civilization when natural building materials such as stone and timber were not available. Sumerians, Assyrians, Egyptians, and Hittites have used Adobe materials in house constructions and monumental structures such as stables, palaces, castles, walls, and towers since prehistoric times. And what are these basic steps of brick making? The first one is clearing a large open space for the bricks to be dried. Second, finding and digging up appropriate sediment. And third, mixing the sediment with water and tempering material. Fourth, putting the mud into wooden molds and scraping off the excess. Fifth, after a batch of bricks is made, leaving them to dry for about a week, turning them on alternate sides. Walls could be laid using the same bricks as were employed in the constructions of walls, or could be created with bricks made specifically for the job. In the latter case, the bricks are thinner and lighter and could even be wedge-shaped rather than rectangular to facilitate the shaping of the vault. Specialized vaulting bricks often were scored with finger marks when they were produced, a feature that increased the bonding of mortar to the bricks during constructions. The history of the mud brick buildings dates back to about 9,000 years ago. Adobe is widely used as a building material in many developing countries because of its low cost. Its use is more common, especially in towns with poor people. Mud brick is a building material obtained by mixing the appropriate clay soil with straw, other vegetable fibers, or some additives, kneading the mixture with water, shaping it by pouring in the molds and drying under atmospheric weather conditions. Historic houses and monuments made of earth are very difficult to protect. Mud brick structures are among the raised structures that are adversely affected by weather conditions such as rain, snow, and wind. In time, degradation occurs in Adobe structures due to three main reasons: physical, chemical, and biological. The most important source of the degradation of the Adobe structure is water and moisture. Physical degradation. The Adobe structure is damaged by pulling up the rain and snow water accumulated on the floors by capillary means. Soluble salts found in high amounts in the soil used in the production of Adobe materials cause the Adobe structure to crumble and deteriorate with the effects of the water and moisture. And chemical degradation, rainwater entering the wall with the effect of wind and spreading with capillarity also starts to dissolve different amounts of salts in the artificial or natural materials on the wall. Dissolved salts create erosion on the surface, destroying the surface protection and also causing appearance defects. Waste gases, industrial wastes, various cleaning chemicals in the air in the city atmosphere cause difficult and costly damages on the building shell. In general, smoke, sand, dust, sulfur dioxide, and sulfur monoxide are the most destructive factors in the atmosphere. Biological degradation. The straw and other plants used to make Adobe are food source for ants and other creatures. Reptiles, rodents, insects, bacteria, fungi, and plant species living in the soil environment play an active role in the deterioration of Adobe structures. For example, life forms fed by the roots of mold bricks plants open channels to reach the roots of these plants, causing the Adobe to weaken, fragment, and corrosion. Flowering can also be seen when seeds that come naturally between the fine capillary cracks formed over time in the Adobe structure. Biodegradation depends on environmental factors such as colonization of bacteria, lichens, moss, fungi and algae, humidity, light intensity, air pollution, climatic conditions, porosity and mineral components, and biological receptivity of the substrate. And what are the effects of climate change on buildings? Climate change is the most realistic threat to historical heritage in the world, as we know. Most of the current research on the effects of climate change focuses primarily on agriculture, biodiversity, health, and water research. The consequences of climate factors on the built culture heritage are multifaceted and difficult to assess for a number of reasons, such as the complexity of behavior patterns of building materials in historic buildings and the difficulty of measuring the mechanisms of interaction with the current climate. Climate change can affect cultural heritage mainly through seasonality differences and the behavior of climate and extreme weather conditions. Hence, it can increase the risk of damage to cultural heritage. However, while the wall of Dijon's Old Town is a World Heritage Site, the technological knowledge, rituals, and social structures that are part of the yearly renewal of many earthen buildings in the city are being eroded by multiple complex, interlinked social and environmental factors. Changes in architectural practices caused by the increasingly unpredictable climatic regime have impacted deleteriously on traditional building methods, specifically contributing to the mud bricks used today being inferior in quality and durability. A reduction in rainfall and fish stocks has also degraded the quality of the mud used since the latter requires the use of calcified fish bones to make it resilient to extremes of climate. Arguably, one of the most iconic forms of African heritage at risk from climate change is traditional Adobe architecture, including the technology to build it. Although temperature differentials and erratic precipitation regimes have a direct impact on Adobe buildings, other multiple interlinked and often indirect factors mediated by a changing climate are already undermining traditional Adobe building methods. Building in Adobe is nevertheless one of the most sustainable forms of architecture in Africa, as seen in the picture. And the water moisture destructions of the Adobe structure, water brings dirt and pollutant particles trapped or adhered to the facade material, parapets or protrusions. Flooring, abrasion, part rupture, and detail loss occur on building materials due to the effect of water and moisture. The water rising from the ground causes the outer surface plaster to fall off, the physical and chemical structure of the walls to deteriorate as a result of the evaporation of the salts it carries on the facade surface. In general, Adobe buildings deteriorate mainly due to excessive moisture in the form of rainwater, melting snow, or groundwater, due to many indirect mechanisms such as moisture, freezing, thawing, and salt crystallization. Mud brick can damage as structure, and Adobe degradation cannot be attributed to a single degradation mechanism. Most decay processes occur simultaneously and at different scales, but moisture is often involved, as seen at figure 1. Rainwater falling on the facades with the effects of the wind causes moisture on the interior facades by entering through the cracks or grab on the building materials. Water coming to the wall surface causes the facades to get wet. This shortens the life of the building over time. Moisture damages material of the building, property, and the people. It causes metal materials to rust and corrode. It causes the wood material to crack, rot, and swell. It causes exfoliation in capillary materials due to freezing and blooming in plasters. Since humid air is conductive, heat and sound transmissions increases. It causes rheumatism and joint pain in humans. Biological degradation in Adobe structure. Not only molds or lichens, but also fungi, lichen, bacteria, and higher plants develop in Adobe structures with the increase of moisture. It's seen that germination is coming in rainy regions. In more arid climates, a few leaves of xerophiles on the surface can be supplemented with large roots several feet tall, causing massive cracks in the wall in search of water. Once rotted, they leave holes for water infiltration primarily. Animal life can also cause damage to these structures. For example, birds build their nests on adobe walls. In the Andean Venezuela regions, for example, one species of wasps digs smaller but more holes for their nests. Historic earthen buildings in Central West Argentina have provided a valuable research for recent material culture studies. Without adequate maintenance and repair, it has become inevitable for such buildings to suffer damage caused by physical or biological processes. The agent B that caused biological damage to the soil walls of Capayan ruins in La Regia, Argentina, has been identified as centuries muralis. The adobe wall and the degraded area are continuously observed, measured, and photographed, as you see at the figure 2. The weight of the material lost from the wall due to biological degradation was estimated to be 729 kilograms of soil, and the destruction in the parts exposed to the invasion reduced the thickness of the mud brick wall by about 7 centimeters compared to the parts without bee nests. It has been observed that the nest shells are generally vertical or slightly inclined and towards the wall up to 12 centimeters from the wall, as you see at the figure 4. This study emphasized that adobe walls are not only damaged by water conditions, also exposed to biological degradations. At another study in Brazil, representing the first stage of the production status of Brazilian coffee beans, the presence of fungal communities in biofilms growing on the earthen walls of rural and semi-urban historic buildings in the upper basin of the Paraíba do Sul River have been described. Significantly high fungal biodiversity has been found in compacted soil. Fungal biological degradations is one of the most important degradations mechanisms that are effective in increasing loss of aesthetic and functional properties of building materials on both organic and inorganic substrates. And at this sample, 16 fungal isolates were identified as a result of the study. Conclusions and discussions. As a result of the researches, the first studies of biological degradation in adobe structures made an important contribution to the broader understanding of such a phenomenon on the context of cultural heritage. The fungal colonization detected exhibits both acidifying and cellulitic activity, albeit to a different extent, leading to a potential risk of damage, compromises the mechanical stability of soil structures by growing inside soil structures, feeding on organic binders and fibers, and releasing aggressive metabolic byproducts. Also, some fungi detected have not been previously reported for buildings. Their presence suggests that some specialists in growing in the soil and getting nutrients from it, while others prefer to grow on vegetative material and participate in organic matter decomposition. Therefore, it shows that they can be found easily in the soil. For the walls of Kapayan ruins to become the preferred nesting habitat for Centris muralis, there are likely two main factors: the availability of food close to the nest and the large homogeneous surface area where the structure creates a habitat as attractive as nesting. Inside the nest, abundant pollen was found from Lara sunephalia and Lara divaricata, indicating that these plants provide the main source of wild flowers that bees can feed on. The corrosive effect of Centris muralis is thought to be bidirectional. Insects actively extract material from the mud brick structure while digging deep hollows to build nests, and voids weaken the mud brick structure, and some parts have collapsed as a result of the outflow. Biodegradation of the mud brick wall with muralis is not abrupt. Its harmful effect is a long process seen in high density spaces. Due to the abundant state of these ruins, the structure and strength of the buildings have deteriorated. It will be more possible to prevent this biological degradation process with minimum maintenance by blocking the holes created by the bees in the Adobe structure and using natural or artificial repellents and deterrents. However, when the presence of a significant number of cells threatens the stability of the entire wall, removing the nets and clearing the affected area will work better to perform consolidation tasks. Nowadays, since the positive effects of the soil in terms of building, physics, and human health began to come to the agenda, research on mud brick houses and Adobe construction systems have increased. Houses built by improving the negative properties of Adobe material made from soil using different production methods or changing construction systems have started to come into our lives again. And in Europe and North America, research into the effects of climate change on historical heritage, how to mitigate more frequent extreme weather events, and how to implement efficient sustainable adaptation planning are now the main focal points of historical heritage literature. Without significant intervention, it is inevitable that some of the most important cultural structures in the world will disappear as a result of direct and indirect effects of climate change in the coming years. Thank you for listening. I know I was very fast because I have small kid who's waiting me.
Thank you very much, Ayşe DOLAR, for this interesting presentation. I kindly ask our audience to notice the questions. We will have the possibility to answer them after the presentations. We have two more. We will continue now with Begüm Diker. She prepared a paper with Fatih Yazıcıoğlu from Istanbul Technical University about an assessment on thermal comfort in Adobe structures. Begüm Diker is from Doğuş University in Istanbul.
Hocam, the program is changed, so it's my turn, I think.
Okay, I didn't get the information about that. Seda Nur Alkan. She's not on my program. Ömer.
Hocam, evet, Seda Nur Alkan olarak güncellendi program. Sizdeki muhtemelen eskisi.
Tamamdır.
Seda Hoca var.
Evet, Seda Nur Alkan. O zaman bu arada sorayım. Ondan sonra da Ganesh'in sunumu var. Doğru mu?
Evet, aynen öyle.
Evet.
Begüm Diker sunumu o zaman iptal.
O yarın.
Yarın.
Evet.
Tamam. Bunu da düzeltmiş olduk. Seda Hanım. Teşekkürler. O zaman sunum sizin.
Teşekkür ederim. Ben ekranımı paylaşıyorum o zaman. Can you see my screen now?
Yes.
Okay. Good afternoon, everyone. I hope you are all well in this pandemic situation. This research is about the hygrothermal performance analysis of traditional timber frame Adobe infill houses in Turkey. The presentation follows these parts. Firstly, I'm going to present the aim and method of this study, and then it will continue with the case study and conclusion parts. The aim of this research is to examine the hygrothermal performance of traditional timber framed with Adobe infill walls in order to analyze their humidity-based problems. The research has two main steps. In first step, start with the literature review about the traditional timber frame with Adobe infill facades and continue with the hygrothermal performance criteria that we can adapt it to these hygrothermal simulation processes. And then in the second part, the case study, first we determined the 4 different wall types from the comprehensive agenda of Turkey. And then we made hygrothermal simulation model by Delphin. As we all know that the Turkey has a comprehensive agenda of traditional timber frame houses and they reflect the cultural, historical, architectural and social features. During the historical period, we see that since the establishment of Turkish Republic in 1923, the materials and methods of construction have transformed into a new approach because of the urbanization effects in Turkey. And we see so many apartment buildings that dominate the urban areas and city center. It's thought that the concrete is a very similar and simple way of design to supply the energy and cost efficiency during the design and construction processes. As a result of this process, we see that traditional timber frame houses become the cultural heritage parts in terms of being the elements of the city center. And at the beginning of the 19th century, we see that sustainability become really important issue. And in terms of this issue, timber frame houses have become really important and crucial issue because of their environmental friendly behavior. And in Turkey, beside this sustainability issue, after the earthquake in 1999, in some cases, we see that these buildings perform well under the seismic loads when we compare them to the concrete frame buildings. And there are many studies about this issue in the literature. And also there are some thermal performance research about the traditional timber framed houses in Turkey to investigate their energy efficiency. However, to understand the energy efficiency of this building, it's not only enough way to understand energy efficiency of this building just to analyze the thermal performance. Besides the thermal performance, it has to be considered the hygrothermal performance of them because Hydrothermal performance analyze the three important criteria, which are heat flow, moisture flow, and air flow as a whole. When we look at the Adobe as a building material, it's an important role depending on their environmental friendly and natural based feature. And for hydrothermal performance criteria, it's an earth-based materials that can regulate the temperature and relative humidity inside of the buildings. And that situation is expressed as cool in summer and warm in winter throughout the history. And this situation creates comfort conditions inside of the buildings. Here we see the case study representation with drawings. In left side, you see the red rectangle that shows the simulated parts. And right side, we see the 4 different wall types layer. And the first one, we have plaster layer inside and no covering layers on outside. In second one, we have both inside and outside a plaster layer finishing. And the third one, again, we have the letting and lime plaster layer finishing inside and no covering layers on outside. For fourth one, we have the plaster layers in outside and letting and lime plaster layer in inside. These examples are selected to understand the effects of these covering layers differentiation on hydrothermal performances. And for hydrothermal performances, we take the KERPİC weather condition for outside, weather condition data. And for inside, the indoor temperature is arranged 20 Celsius degree and relative humidity is arranged as 50% for simulation according to DIN EN 13788. And for each example, simulation process cover a whole year, start from January till December. Here we see the 4 graphics of the walls that indicates the temperature and relative humidity relationship. The black lines show the temperature and the red one shows the relative humidity value. And commonly it seems that when the temperature getting lower, the relative humidity getting higher throughout the winter season. That means that when this relative humidity layer just exceed to 18% and very close to 19%, it may occurs that humidity-based problems, and we see that this situation may occur for fall selected examples. Here we see the relative humidity values for 4 wall types during a whole year. It's automatically stretched by the simulation program to show the whole process as a graphics. And in these graphics, we commonly see that first one and the third one, second one and the fourth one has kindly same situation. Which are for the first one and third one, this means that in the covering layer inside, which plaster layers, we see that there is a values differences between the outer surface and inside part is very huge. That means that the surface of the plaster layers has become has an important problem about the humidity throughout the years. And for the second and fourth one, we see that the relative humidity differences may occur the inside part of the walls, in especially Adobe infill part. And this may cause the humidity-based problem that infill part and also their intersection point with the wooden studs So in that case, we have the humidity-based problem, especially in the middle of the wall system. And also the, again, the plaster surface inside, we see the, again, the level differences of relative humidity. And again, we have some moisture-based problem on this plaster layer surface as well. And these graphics shows the moisture content during the year. And as it is seen that, especially in wooden parts of the wall, which are wooden studs and letting parts, we see that the moisture content getting higher in these parts. And during the year, especially in long term, it may cause a moisture-based problem in these parts also. When we come to the conclusion, we can say that the traditional timber frame with Adobe infill has really critical issue for energy performance and cultural values. And they are important because of their natural-based construction material usage. And according to these hygrothermal performance analysis, it is investigated that even if the layers are varied, there may be humidity-based problems for these selected examples, especially in the intersection point of these materials, and their relationship between each other should be reconsidered. And as it is seen that in long term, these moisture accumulation may cause the durability problems, and they also affect the seismic performance of these examples also. And at the end, we try to make awareness about the importance of hygrothermal performance of these examples during the conservation and restoration project, because these examples are really important as a part of cultural heritage. This is the end of my presentation. It's a pleasure if you share your comments and questions. If you prefer, you can contact me via this email. Thank you for your attention.
Okay, thank you very much, Seda Nur Alkan. We have one more presentation and then we can have our discussion round. The next presentation is about the paper influence of randomly distributed geofibers with fly ash on the performance of the soil. This paper was prepared by Ganesh Srekeshava from Visvesvaraya Technological University in India, Prakhand from Kathmandu University in Nepal, Vasuki also from the Visvesvaraya Technological University, and Ganesh will present the paper now. Is Ganesh with us?
Yes, am I audible?
Yeah, yes, we can hear you.
Is my computer screen visible?
The screen, for me, not at the moment. No, the screen sharing is not ready at the moment.
Okay, just a minute. Here I'm facing some network related issue due to rain.
Yes.
Just a minute, sir.
We are waiting. We have already.
Yes. Is my screen visible now?
No.
You should choose the PowerPoint for sharing.
Yeah,
yes,
now
it
we can see it. Now we can see. You can start the presentation. Yes,
thank you.
Yes, we can see it now. Please, the floor is yours.
Yes, thank you. Hello, everyone. I'm Mr. Ganesh CR, working as an assistant professor in Jyoti Institute of Technology, affiliated to Vishweshwaraya Technological University, India. My co-authors are Mr. Sri Keshava KS and Dr. Prachandaman Pradhan and Mr. Vasuki BM. So today I'm going to present my work titled Influence of Randomly Distributed Geofibers with Fly Ash on the Performance of the Soil. So let us start with the introduction.
Excuse me, dear Ganesh, can you open your camera if it is possible?
Sorry?
Can you open your camera?
Oh, just a minute. Yes. Yes, let us start with I will start with the introduction. See, my research work is mainly based on improving the CBR performance of the soil, that is California bearing ratio. See, in many road construction, what we will observe here is, even though soil is good with some of the other properties, it will fail in giving good CBR value. So in this research, we have made an attempt to improve the CBR properties of the soil. So what is meant by CBR or California bearing ratio? So CBR is a measure of resistance of a material to penetration of standard plunger under controlled density and moisture conditions. So how we are going to maintain the controlled density and moisture condition in laboratory condition is by doing the Proctor compaction test. So in our research work, we have chosen standard Proctor compaction test in order to maintain the controlled density and moisture conditions. See, this CBR test can be conducted on both remolded soil sample as well as undisturbed soil sample. See, if the original soil structure got changed, then it is called remolded soil sample. So in our present work, we have conducted a CBR test on remolded soil. So what we have done in this research work is that in the present work, we have carried out a basic geotechnical test as per Indian standards 2720 in order to know its index and compaction properties. Then we have conducted California bearing ratio test in accordance with IS 2720 Part 16 1987, both in soaked conditions as well as in unsoaked conditions. Why we have conducted in both the condition is, whenever we are constructing a road, it is subjected to all types of weathering. It may be summer or it may be rainy season. So we have checked the CBR performance both in soaked as well as in unsoaked conditions. So what we have done here in order to improve the CBR value of a unreinforced soil is, here we have used the polypropylene fibers as a reinforcement. We have randomly distributed these geofibers in combination with fly ash at various combination in order to improve its performance. So after determining the CBR value by using the correlations, we have determined the resilient modulus of the soil and modulus of elasticity of the soil. So the resilient modulus is nothing but it's an indicative measure of a subgrade material stiffness. So by using IRC 37-2012, the resilient modulus is determined using these two equations. If the CBR value is found to be less than or equal to 5%, then we are going to use the first equation, that is MR is equal to tan into CBR value. If the observed CBR value is greater than 5%, then we are going to use the equation MR is equal to 17.6 times the CBR into 0.64. So once we determine the resilient modulus, using that resilient modulus value, we are going to determine the modulus of subgrade reaction using the equation K is equal to 2.028 into MR. So at last, after all this experiment, what we have found is the CPR value got improved when compared with the unreinforced soil. So the materials used in the present work is mainly fly ash. So fly ash is the byproduct which is obtained during the burning of pulverized coal during electric generation power plants. So this fly ash is a pozzolanic material, means it contains both aluminous and siliceous material, so that it will develop strong bonding along with the soil in the presence of water. So, and we have used polypropylene fibers as a reinforcing element along with the soil. The diameter of this polypropylene fiber is 0.3 mm, which is cut in lengths, which is ranging from 1.5 centimeter to 2.5 centimeter by maintaining an aspect ratio of 50 to 80. So we have varied these randomly distributed polypropylene fibers in various percentages. We have considered 0.25%, 0.75%, and 0% when there is no fibers. So we have used the locally available soil near our college campus. The soil is collected by means of open excavation at a depth of 2 meters from the natural ground level. So these are the pictures which shows the materials that we have incorporated in our research work. The first one is the fly ash that we have used in our work, and these are the polypropylene fibers. Next, when it comes to methodology, what and all we have done is the basic geotechnical test, all the index properties test like liquid limit, specific gravity test, then plastic limit test. That tests we have conducted in accordance with IS 2720 in order to know its index properties. Then we have conducted compaction test. We have chosen standard Proctor compaction in accordance with IS 2720 part 7 1980. The purpose of this standard Proctor compaction test is to know the maximum dry density and optimum moisture content for various combinations. Then we have conducted the CBR test both in reinforced and unreinforced conditions. For reinforced conditions, we have considered various combinations. All the tests are conducted in accordance with IS 2720 part 16 1987. We have conducted both in the soaked condition and unsoaked conditions. So in case of CBR, we have used the remolded soil sample. After preparing the soil samples by using a standard plunger, we have applied the load using the standard CBR testing machine. See, this is the actual methodology. This picture shows what we have done. Initially, we have taken the soil. From the compaction, we know what is the maximum dry density and optimum moisture content. We have added that much amount of water to the soil, and we have taken the fibers. Then we have mixed it thoroughly in order to get a uniform mix. Then we are compacted in the standard Proctor mold. So for soaked condition, we have kept the mold inside the water for 2 days. Then for unsoaked conditions, we have conducted the experiment immediately. So the figure 5 shows the experimental setup for conducting the CBR test. Then let's come to results and discussions. We have conducted various basic geotechnical tests in accordance with IS 2720. So these are the results found. The specific gravity of the soil is found to be 2.56. Then the liquid limit of the soil is found to be 42.14%. Then the plastic limit is found to be 22.46%. Then plasticity index is found to be 19.68%. Then the compaction results, the OMC and MDD is found to be, this is for unreinforced soil. It won't contain any fiber or fly ash. So for unreinforced soil, we have got optimum moisture content value as 14.659% and the MDD value as 1.862 gram per cc. So the table 2 represents the various values, these compaction results for various combinations. See, we have used 3 combinations. That is 0.25% of polypropylene fibers along with 10% fly ash, then 0.5% of polypropylene fibers along with 15% fly ash, then 0.75% of polypropylene fibers along with 20% fly ash. So these are the optimum moisture content and maximum dry density values found for various combinations. So from the table, it is observed that for unreinforced soil, we have got more MDD value as well as OMC value. For after reinforcement, we can observe the OMC value got reduced. So the reason is very simple. The fiber will absorb the water. The density is got decreasing because the specific gravity or weight of the fibers and fly ash is less than the soil. So this is the reason. So this represents the graphical variations for various combinations. Then when it comes to the experimental results of CBR, this is for unsoaked conditions. For unsoaked conditions, it is found that for an unreinforced soil, we have got a CBR percentage of 2.109. As we increase the fiber percentage as well as the fly ash percentage along with the soil, in case of unsoaked conditions, it is found that it goes on increasing. So for soil along with 0.75% of polypropylene fibers and 20% fly ash, it is found that the CBR value is almost 5 times greater than the unreinforced soil. So by using correlations, we have found the resilient modulus value as well as the modulus of subgrade reaction value. The maximum value of modulus subgrade reaction is found to be 164.80 megapascal per meter. So these are the results for unsoaked conditions. When it comes to the soaked conditions, we have found that the CBR value is lesser than the unsoaked condition, but we have observed an increase in value of CBR for the reinforcement conditions. See here, for the unreinforced soil, we have got a CBR value of 3.498%. But for reinforcement condition, the optimum combination for soaked condition is found to be 0.5% of polypropylene fibers along with 15% of fly ash. Here we observed that there is increase in CBR almost 1.5 times the unreinforced soil. Similarly, by using the correlations, we have determined the resilient modulus as well as the modulus of subgrade reaction. The modulus of subgrade reaction for the optimum combination is found to be 104.20 megapascal per meter. So these are the results. And this is the graphical representation of load versus penetration values which got observed during the conduction of CBR test. So the first graph, that is figure 7, represents the graphical variation for unsoaked condition, whereas the figure 8 represents the load versus settlement variation for soaked condition. See, in figure 8, for soaked condition, the optimum combination is found for soil along with 0.5% polypropylene fibers and 15% fly ash. So this is all about our experiment. So from all the experiment results, what we have found or what we can conclude is, from the various studies, it indicates that the mixing of polypropylene fibers along with the fly ash will increase the strength of the soil so that it becomes suitable for using as a subbase material in case of road constructions. So then when it comes to CBR results, the CBR value for unsoaked conditions is found to be greater when compared with the soaked conditions. So the maximum CBR value observed for unsoaked condition is 10.956%, whereas for soaked condition, the maximum CBR observed is 5.334%. and the optimum combinations of polypropylene fibers as well as fly ash that should be used along with the soil is found to be 0.5% and 15% in case of soaked conditions, whereas for unsoaked conditions, it is found that 0.75% and 20%. So using the CBR value, we have determined the resilient modulus. So the resilient modulus, which is determined both in unsoaked as well as in soaked condition, is found to be 81.26 megapascal and 51.38 megapascal. This is for the optimum combinations. Then using the correlations, we have determined the modulus, that is resilient modulus and modulus of subgrade reaction value. So the modulus of subgrade reaction value for both unsoaked and soaked conditions was found to be 164.80 megapascal per meter and 104.20 megapascal per meter respectively for optimum combinations. So this is a purely experimental results based on CBR test. So these are the references that I have gone through. So thank you everyone for your patient hearing. I thank the team KERPİC for giving an opportunity to present my work.
Thank you very much, Ganesh Sir. We
have some questions.
We can start the question round. The presentation of Negar Javadi is unfortunately cancelled because of COVID-19 health problems. We send from here our best wishes and start with the questions. We have already a question and also the answer in our chat. We had the question from Senem Kahraman: does gypsum additive in Adobe wall help reduce biological deformation? And Ayşe DOLAR answered her in the chat already. Unfortunately not, because the mineral needed by living organisms will be still in the structure. Our structures are not only will be contained with gypsum, she answered. And we have also the question from Merdat Hecazi to Sedanur Alkan. Actually, he has two questions to her.
If Professor Hecazi here, if it is possible, he can ask directly.
Yes. Professor Hecazi, can you hear us? I didn't hear.
So him, but now he's not maybe here.
Maybe he's not available. The questions were to Sedanur Alkan. First one was, which software did you use for hydrothermal analysis? And the second one is, how did you examine the hydrothermal properties of the materials of each layer?
As I mentioned in the presentation, the program is Delphin from Dresden University in Germany, and the program automatically used the data for each materials during the simulation processes. It has a specific data for the hydrothermal performance analysis.
Professor Hecazi is now with us. Do you have other questions about this topic?
Yes, thank you very much. I hope that you hear my voice.
Yes,
right?
we can hear you.
Okay, nice to meet you. Actually, I couldn't see the first section of the presentation because online class, that's the reason. At the moment, one of my colleagues is working on the same subject, hydrothermal analysis of Adobe buildings. And also Delphin is one of the best one, which is on the way at the moment. My question is it your personal research, or is it a project you're doing, or what is that?
It's just the beginning part of my PhD research, just a small part. And
okay, that's
for
great.
the hygrothermal performance, generally use two programs, which is Delphin and which is Woofy. And in the literature, we mainly see these two simulation tools to analyze the hygrothermal performance of the walls especially.
Okay, that's great. Because at the moment, one of my colleagues is doing the same thing, the same project. If you don't mind, I will connect you to my colleague, because she also is using Delphi and the other one. And I think maybe out of your collaboration or change of information, you can get a better result. Is it okay if I connect you to my colleague?
Of course, you can contact me.
Okay, okay.
I will our just the experience with us.
Okay, thank you very much. It was very nice, and your presentation was so good. Thank you very much.
Thank you too.
Yes, one of the nice fruits of this international conference will be a collaboration with Iran. Thank you very much, Professor Hejazi. We don't have any questions in the chat, but if you want, you can ask.
Yeah, I have a question to Professor Hejazi, if it's possible. Yeah, yeah. Professor Hejazi, thank you so much for your presentation. It was really wonderful. I would like to ask you two questions. The first one, you said that when you observed the underneath Adobe, when it was subjected for drying and wetting cycles, the strength increased, and the bearing capacity increased. So do you have any scientific explanation for this phenomenon?
Well, actually, it was so amazing to us, because when we wanted to test wet Adobe, when we put the same sample in the water, after 10 seconds, it was decomposed.
Yeah, disappeared.
I would think that the instant pressure, which that side was the basement of the building, and the wall is about more than 10 meters high. I would guess that the pressure, the compression of the upper part of the wall somehow has prevented from the decomposing of the Adobe, and maybe after it has been dried again, maybe its compressive strength has been increased. We have not done any experience for that, but maybe in near future I will do such a experience. Maybe that might be the answer.
Okay. My second question is, I noticed that when you showed us the production of Adobe, you produce it into like a greenhouse or something like that, or semi-shaded, semi-closed area. Is it because that you are not using straw? You are, or what?
No. Actually, as I told, we have two types of roof. One type could be flat or straight, okay? Therefore, we give them very slight slope for rain. But when inside the house, we want to have arched roofs, okay? Therefore, on the top, the shape of the roof would be domical, okay?
Yeah, maybe I didn't clear my question. My question is regarding, my question is regarding the production process, because one day we worked in Egypt with Adobe, and because the weather was very hot, we don't want to expose the fresh produced Adobe to this extreme hot, to not deliver any cracks. This is why we cover it under plastic sheets to limit a little bit the evaporation process. This is why I asked you, because I didn't notice that you are using straw with the mixture. Are you using straw?
I should explain. In BAM Citadel, in the summertime, the temperature goes up to 40 or sometimes 50 degrees centigrade, which I think is similar to Egypt, maybe in some parts. Okay, we use some sort of shading for that. It means that we produce under the shade, and sometimes we use a straw. A straw would help to prevent the cracking. But the main thing is we do not allow sunshine directly goes onto the product. As long as it is inside shadow, that would be enough. At least in Iran, it's the same.
Did you ever try to produce it without straw, just depending on the grain size distribution?
Yes, sometimes we use a straw, sometimes we don't use. It means that cracking is not very much related to a straw, but it is more related to amount of clay which is inside soil. Okay.
Yeah, this is what I mean by depending on soil structure.
Exactly. Yeah. And I should give you information that me and my colleague in my university, we have invented a method that we are able to prevent cracking of the Adobe. But you should wait until we publish our paper.
Yeah, I'll be anxiously waiting for such scientific material, because you know it is one of the disadvantage, the most disadvantage of Adobe, that we have to use a straw to prevent developing of cracking. If you could solve this without using the straw, it would be wonderful, really.
Yes, yes. Well, I think we can start a collaboration from Iran and Egypt, if you agree. And I send you my email address at the moment. If you could send me, Muhammed, an email, then we can start our collaboration from next week.
For sure, it would be my pleasure. Thank you so much. But for me, I'm not specialized in Adobe. I'm specialized in compressed earth block.
You are sorry?
Specialized in compressed earth block.
Oh, it's a bit dangerous. I'm sorry, but no problem. I think we could find something in common. Okay.
Yeah. Tomorrow we'll have my presentation, inshallah.
Okay. I was just joking. Don't worry. We will start. No. Okay. Thank you for so much. Thank you for your questions. Thank you.
Thank you very much, Professor Hijazi and Mr. Al-Rafai.